First, I wanted to thank the organizers for giving me the opportunity to present my work. It's a real pleasure to be sharing my work with you. So I'm Natalia Rossignoli. I'm a PhD student at the National University of La Plata in Argentina. And my PhD supervisors are Dr. Romina Di Sisto and Dr. Gabriela Parisi. I belong to the planetary science group called Origin Group or Group Origen at the Faculty of Astronomical and Geophysical Sciences in La Plata. And today I'm going to present our results on modeling impact cratering on Titan, but this is part of a larger work where we have studied all the Saturnian satellites and plan on continuing studying other satellites in the outer solar system. So, as you know, Titan can be considered kind of a supermoon in terms of its size and the complex chemical environment it has presented. And because it is the only satellite where a dense atmosphere has been detected so far, and where the presence of liquids have been confirmed, it poses a very challenging and interesting environment where to test our cratering model. So before Cassini arrived at Titan, we could detect some of its features on the surface, but most were hidden by the atmosphere. And also, before the radar images were made available, we expected to find thousands of craters on its surface, like the ones we could see on similar satellites like Callisto, the image on the right. But instead, once the radar images were made available and the crater counts could be calculated, we found surfaces like Xanadu region on Titan, which is the image on the left. So actually, performing a crater count on Titan is pretty challenging, as you can see. So the Cassini radar images covered 69% of the surface, and in that area, only 90 impact craters have been detected so far, as they are presented in the work by Joshua Edgepeth and collaborators from this year. And in addition of the scarcity of impact craters, what we have seen is that impact craters are shallower than expected, and they present signs of erosion, clear signs of erosion. And in addition to that, we now know that the distribution of these craters, as we can see in this global map of Titan, is located in a way that most of the impact craters are located near the equator. So why is this happening? Well, because of the main lakes and liquids are located near the poles, it could be because the craters on the poles are no longer detectable. But this is a matter of discussion. So each of these red circles represents one impact crater. And well, how do we model the impact cratering? Well, first we model the impactors. So we take the main impactors to be the heliocentric impactors, which are populations, specifically the Centaurs, which come from a region beyond Neptune, which is the scatter disk, and they migrate inwards into the solar system. And as they migrate, they can both impact the satellites and the planets and their satellites. And we have been performing a series of dynamical evolution simulations where this year we have published the latest simulation where we use all the updated results on the observations of the scatter disk objects. And then we built a size distribution model where we consider that the largest members of the Centaur population have this form of the power law. And for this index, 3.7, there is a good agreement in the literature, but for the smaller members of the Centaur population, those who are 100 kilometers in diameter or less, there is a very high uncertainty on the power law index. And we take it to be 3.5, the value, And we have already tested this model in the other Saturnian satellites, and this has worked well in predicting the largest craters. So we will see how it worked on Titan. For the collisions, our model considers the solar system in its current configuration, and we use an approximation of a particle in a box approximation, and we consider all the collisions over the whole solar system age. And to relate the impactor diameter to the crater it forms, we use the well-known Holzapfel-Hausen equations from 2007 and the parameters presented in Kraus' work from 2011, as Patricio also mentioned. And this is a very well-known equation, but because Titan is so large, most of the craters will be under the gravity regime, will be formed under the gravity regime, and most of the craters will also be complex, which means they have terraced walls or central peaks and so on. So this is the limiting value for the crater between a simple and complex crater, and this will be the form for the final diameter of the complex crater. And for the atmosphere model, we chose to use the work by Fulcinioni and collaborators from 2005, where they presented data collected by the Huygens probe as it descended on Titan's surface. It collected the data on the atmospheric density profile. So now we have the density profile, and we know that at the surface, Titan has an atmospheric density that is 4 times larger than on Earth. So no impact cratering model can be completed without considering this factor. And then for the atmospheric effects, we used the Korikansky and Salne model from 2005, where they present several effects, and we chose to use what we consider to be the main effects, which are drag of the impactor and ablation of the impactor. And these coefficients here are the ones that are presented in this work. And last, we calculate the surface age or the surface chronology, and we use the results presented in this Stones and Arby from 2016, where the impact cratering time dependence is fitted with a logarithmic function. So as you can see here, the age for each crater diameter will be given by this equation that that depends on the ratio of the cumulative number of observed craters and the cumulative number of calculated craters. And this is the solar system age. So here I will present now the results. Here we see the impactor velocity as it approaches Titan's surface. And as you can see, all impactors start with the same velocity, and the 5 different curves show different impactor sizes. As you can see, a large impactor of about 10 kilometers of radius won't even notice that there is an atmosphere, as it could be expected. But as we go down in size of the impactor, what we can see is that for impactors that are 100 meters in radius or less, the atmospheric effects will be larger, and impactors that are 10 meters in radius or less will be slowed down to a point where they come to a halt. And in our model, we do not consider them to form any craters. As for the results on the impact cratering model, here we have the observed craters, the 90 observed craters as they are presented in this work. And this is the cumulative number of craters per square kilometer, or the size frequency distribution over the size of the crater diameter. And as we can see here, the curve flattens as we go to smaller crater sizes. And this is because Titan has a scarcity in general of impact craters, but especially regarding small craters. So here are our results. The black curve shows what are our results for an airless Titan that is not considering any atmospheric effects. And the brown curve shows our results with a model that takes into account the main effects I mentioned before. So as you can see, there is a very good agreement for the largest craters on Titan. Most of the largest craters on Titan are very well predicted by our model, and as we go to smaller sizes of craters, we have an overestimation in our model related to many factors, as I will mention in a bit. As for the Melbra crater, which is 400 kilometers in diameter, we think it may be primordial in the term that it may have formed during the late heavy bombardment phase. So our model starts with the current configuration of the solar system and does not take into account this phase. So we could not predict this crater. So this is our table for the results. All the impactors enter Titan with the same velocity. This is before they enter the atmosphere. So it's 10.5 kilometers per second for every impactor. This is the limiting diameter of the crater between a strength and a gravity regime scaled crater. So as we can see, all the craters plotted here are under the gravity regime. And this is the transition diameter between a simple and complex crater. And again, most of the craters plotted here are complex craters. And this is the largest impactor in our model, and this is the largest crater it creates. As for the surface age or Titan's surface chronology, we can see here that the surface age is plotted for every crater diameter. So we see that the largest craters on Titan could be as old as the solar system age. Of course, this is a first approximation model. It's a very simplistic model. But for the smallest craters, we can see that they could be as young as 90 million years. So what are our conclusions? Well, for one part, the low number of detected craters could probably be related to a series of factors, including the atmospheric shielding, which means that the atmosphere prevents small craters to the formation of small craters. And then, thank you, Michelle. And then the strong erosional activity that is shown in every crater, even largest ones, could be indicating that smaller craters will be prone to be more eroded. So we could see here, and there is a work by Nish from 2016 also, that the erosional activity on Titan could be as large as to erase a crater beyond detection. This depends on the rate of erosion, obviously. So the fluvial and erosion and the infilling of these craters could be affecting more the small craters. Then, including more atmospheric effects, we think that we'll end up on stronger shielding effects in our model. But considering the effects I have mentioned, we can already see that for impactors that are 1 kilometer in diameter or less, there is a very strong shielding effect. And for smaller impactors still, it may come to a total disruption of these impactors. So no craters for these impactors. And then as for the age of the craters or the surface chronology, we think that obtaining ages that are as old as the solar system for diameters larger than 50 kilometers could mean that Titan is a primordial object, and craters with diameters less than 5 kilometers could be younger than 250 million years. Okay, that's it. Thank you very much.
Thank you, Natalia. Very, very interesting stuff. And I love that picture at the end. That's awesome.
I can share it.
Looks like Catherine has a question, so hopefully she will be unmuted shortly, and we will go from there.
Thanks, Michelle. I'm glad somebody is looking at this, but I'm kind of puzzled by your results. There are only about 15 craters that are greater than 50 kilometers on Titan. So I don't understand how you're getting an age of 4.5 billion years, since when you look at other icy satellites, you have orders of magnitude more craters. I actually was just looking at Emily's crater counting from the last talk, and she estimated, I'm guessing, like hundreds of craters on Ganymede, which is the same size as Titan. So how do you reconcile the small number of craters with such an old age?
Yes. Well, we plan on extrapolating and going on with this work for all the Galilean satellites as well in the future. But as far as we have worked with this model, we think that it may be related to the fact that our model does not consider any erosion, right? So we only predict all the craters as there will be no erosion at all. And then we relate the age of each crater to the rate of encounters throughout the whole solar system age. Yes, so larger craters will probably be older in general, and if we can predict all of the craters we are seeing, they may be as old as the solar system because they will not be eroded at all. We are seeing all the craters we predicted.
But I find it baffling that you would only find 15 craters over the age of the solar system when you see hundreds
right.
of. No, but yeah, but look at Rhea or look at Ganymede. There are hundreds of craters that size or larger.
We are only considering these centaurs as population of impactors. There are other population of impactors that could be considered for Jupiter, right? Because there are other factors there. We are not considering any planetocentric impactors or any other impactors that are not centaurs and are not included in our simulation.
I would just be very careful with that population then, because if it only predicts 15 craters greater than 50 kilometers over the age of the solar system, it just doesn't make sense. So just take that into consideration.
Yeah, thank you. Thank you for your comment.
All right, there's a question from Ingrid Daubar. She asks, you mentioned you're planning to add the effect of atmospheric fragmentation into your model, but wouldn't that create more smaller craters where your model already overestimates the observations? Or is Titan's atmosphere so thick that the small fragments would get ablated and decelerated enough that they would not form detectable craters?
Thank you for your questions. These are very interesting comments. The fact that the fragmentation could affect an impactor to the point of total disruption has to be taken into account, and we have not performed fragmentation yet because it was very complex to present for this meeting, but we think that because other works state that impactors of 1 kilometer could be fragmented and this totally disrupted by the atmosphere, we think that maybe the result on considering fragmentation will lower down the curve instead of generating more small craters. This I cannot confirm this because we haven't made the simulation yet. Thank you.
Okay, Juan Eschauren, sorry. Dear Natalia, hi, why the impact angle is considered to be only 45 degrees? Can it be more than 45 degrees?
Yes, this is an average angle for the impact. Actually, an impact could be in any angle, right? But we consider this, and it's very used in the literature to consider impacts at 45 because it is the most representative angle, and not the head-on impact, but this at 45 degrees.
Okay, there's one more question in the chat from Ankush. Does resurfacing also have to be the reason for having less smaller craters? Let me rephrase that. I think they're asking, can resurfacing also be a reason for having fewer small craters?
Yes, of course. Our model does not take into account any form of erosion, so we just have to guess which is going to be the strongest resurfacing or renewal of surface process. It could be, yes, perfectly good, but we haven't tested this.
And a follow-up to that, does small crater detection, is that limited by the image quality? So it could be that you're undersampling those small craters?
Where, according to Joshua Edgepeth's work, there may be some lack of resolution for the smaller craters, but we are still seeing or detecting fewer craters that the resolution allows for each small crater.
Okay, and then there is Abedin's question. I am certainly not a specialist on Titan, but are there any rains on the surface? If yes, I believe that the rains would degrade the craters, to which Catherine wrote that it does rain, and it likely erodes craters. See your paper from 2016. But I guess would the rain significantly affect perhaps these smaller craters?
Where, as I understand, but I'm sure she can answer this better, fluvial erosion may affect more the rims than the infilling of the craters, but it could, depending on the rate erosion, erode craters beyond detection of Cassini. But I'm sure she can, she knows better because it's her work.
I'm trying
not sure
to
if
unmute
she wants
her.
to say something. Yeah.
You wanted me to unmute? Yeah, no, and Josh's recent work showed that fluvial erosion did seem to be a bigger factor in degradation of craters on Titan than I originally expected from my 2013 paper, where I thought it was primarily aeolian infill. Yeah, we've seen it rain a couple times on Titan. It does seem to affect the craters, perhaps more so near the poles. And it does seem to affect smaller craters a little bit more, although I think primarily the smaller craters are not there because of shielding by the atmosphere.
Okay, good.
So just a follow-up question. Do we see rain on Titan on kind of the entire surface, or is mostly constrained to the poles?
Catherine.
Okay, am I unmuted? Yeah. So there's a paper by Zabi Turtle from 2011 where we saw clouds form near the equator.
Yeah.
And then the surface darkened and then brightened again. So we took that as evidence for rain in the equatorial regions. It is rare, but it does happen.
Thank you.
Then there was a follow-up question from Juan. Are the equations correct if the impact angle is different from 45 degrees?
Yes, before these results, we tried with a head-on impact because we wanted to test some parts of our model, of the atmospheric effects model. And for a 90-degree impact with respect to the horizon, that is a head-on impact, the results were in agreement with the observations for the largest craters. Yes.